Okay, good morning, everybody. It's just about 11:10 in the morning. People are still coming in. We got 350 of you on the call, so good to see you. I hope you slept well last night. I was up a little late, but I did get a good sleep after all that. Let's share my screen. And we'll talk about what's on the agenda for today. I also need to get the chat window going. And participants list. Okay. There's the chat. Okay, good. All right. There's a thermal camera behind me. You're going to find out all about that. Okay, so on the agenda today, we're going to talk about kinetic energy and gravitational potential energy, also elastic potential energy, and also the work of sliding friction, which we're going to talk about in terms of internal potential energy, I guess, or internal energy. And here's an example of someone going up a hill when you're putting energy in. Getting to the top of the hill where you've got a whole bunch of potential energy, and then rolling down where you're taking that potential, gravitational potential energy and converting it back into speed. Okay, so let's talk a little bit about the midterm assessment 3 that happened last night. So this is the histogram. And what I did on so what happened is that the average for the midterm last night was about 65%, which is a little low. I think it's a little too low. I would like to keep these up in the 70s. So what happened was I went into Excel and I did this equation, which is you either get 100 if you got 10 out of 10, which a few of you did, or you get your raw score multiplied by 1.1. So basically every question you got right was worth 11 points. So if you got 1 right, you got 11, 2 right, you got 22, et cetera, et cetera. 7 correct questions, you got 77. If you got 9 right, you got 99. And if you got all 10 right, you got 100. So it's almost negligible between getting 9 or 10 right. But there is a slight difference there. That's just the number of A's and B's. So basically it's the same. Anybody who got in the 8, 9, or 10 got sort of the A, and then 7 is still B range, but it's 77. Okay. So you might see it twice. You'll see your raw score. I left the raw scores posted on Quarkus so that you can still go in and see which questions you got right and wrong. Hopefully you can see all that. But then the real score is going to be the midterm adjusted score, which someone pointed out. It says it doesn't count towards your final mark, but that's not correct. I also have posted a solutions video. If you go onto Quarkus and look at all this stuff, you'll see that there's something called Midterm Assessment Solutions video on YouTube. It's about 17 minutes. And I just go through and I sort of talk through, I read through all the questions and write out the answer. And you can sort of see my reasoning as I'm going through and doing that. I've also posted written solutions. Only the written solutions are posted if you did the midterm assessment alternate sitting at 10 p.m. last night. I don't have a video for that one, unfortunately. So that's kind of it. That's all I'm going to say about the midterm, since you've got a 17-minute video you can watch about it. Is there any, oh, you can't see your correct wrong answers. Did anyone want to, Jason, did you want to chip in?
Oops, sorry, I guess I accidentally raised my hand. Sorry, okay. Professor.
Anybody else? I'm seeing that on the chat window. Yeah, I understand. I'm having a little bit of trouble with Quarkus making it display, I guess, in a way that is friendly, but someone says, Caitlin mentions there's an exclamation mark next to the adjusted score, which when clicked on says that it doesn't count towards your final grade. So I guess I can try to remove that exclamation point sometime this afternoon, but just don't worry about it. The adjusted grade is the only one that counts towards your final grade. Not the wrong one. Correct answers are hidden. That's weird. Oh, I think I do know how to adjust that. So I think I can do that this afternoon as well, is let you see what the correct answers are. I have to go and make an adjustment to the actual quiz. Again, these Canvas Quarkus settings are a nightmare. And you still are going to drop the lowest midterm of the 5. So the top 4 midterm scores that you get are the only ones that count. The next midterm, yeah. So that's going to be on. This is from Anahas. Good question. That's going to be, I believe it's November 17th. It's coming up in a couple of weeks. So next Tuesday, I think we'll have a practice crowd mark submission where you'll just do a couple like homework like problems, write it out, submit it up to CrowdMark. This is an alternative to using the Quarkus to upload an image. There's another thing, I guess it's within Quarkus, called CrowdMark, where you upload an image. It's the same sort of thing, but you have to click on an email and stuff. And so it's a bit of a different process, but hopefully it'll go more smoothly than the Quarkus one. And then there's a reading week, I think. And the Tuesday when we come back after reading week, there's going to be this midterm on CrowdMark. And it'll just be 2 questions, same sort of format as midterm 2, but just with a slightly different submission process. Can everybody hear me? Arthur's, my mic's not good. Why don't we do this? This is a different microphone, so maybe it's a little better. Sometimes my laptop microphone is a bit better. Okay. I think we're, okay, good. All right, I think we're cooking along here. I think what I want to do is go on to chapter 7 stuff, continue with what we've been doing. And I want to talk a little bit about this work energy principle. It actually turns out to be pretty similar to the momentum conservation. You've got initial plus the work from outside your system equals the final. And that's all it is. It's actually an extremely simple equation. And that's why it's so powerful and you can solve so many questions in it. So you have some work. So what you do is you define a system. You say you've got some initial energy of the system, some final energy of the system, and then that can change if things outside the system are doing some work and adding some energy. Or you could even say you're doing negative work by removing some energy. That also works. Let's do an example. You've got a spring-loaded toy gun, which is used to shoot a ball of mass m straight up in the air. The spring has spring constant k, which we'll talk about in a little bit. It comes with Hooke's law, but the ball has speed vb at point B just before it's leaving, and then it reaches up point C, its maximum height. So I actually have one right here. It's a little ball which is sitting in there. Maybe I should put it right on. You can see it if I put it over here. Yeah, so you can see the spring. It's sort of coiled up, and I have this, which I can pull out. So let's do it over here and we'll see how high it goes. If I pull out the stick that's holding the spring, then it went up to about this height. So then the spring was compressed and now it's into its equilibrium position. So this spring has the property that it can hold some energy. This is its equilibrium. If you compress it, then it's stored some energy, and that stored energy can be used to I don't know, to shoot a ball or to hit you in the eye or something like that. You can make the whole spring jump if you push it down. We've all played with springs, right? And then the other thing about springs, which is neat, is that you can also stretch them and also input energy. So a stretched spring also contains energy and then can fling something. Let's put all this stuff down. So let's analyze this. Using our energy bar thingy. So we define the system to be the ball plus the spring plus the earth. And then the energy conservation equation is EI plus W equals EF. So what you do is you say you've got your kinetic, and then you've got your potential energies of your system. So the spring is in our system, so that's included. And you've got the earth in our system. So that means you include this MGH, the gravitational potential energy. And you just list all the energies and put a little I for initial, and then list all the energies and put little Fs for final. And that's it. And then you just have to plug in, most of these things end up turning out to be 0. Here, W is the work done on the system by things that are outside the system. In our case, the system is the ball plus the spring plus the earth. And so nothing's doing work on those. So we just say work equals 0. So let's consider first the time A to B. So we're going from here to here just before the thing launches. Well, what's going to happen is that the spring will be at 0. Or sorry, the spring will not be at 0. The spring is compressed. And so it has this 1/2 times K times X initial, or XA, I guess, squared. Plus, we can set, this is going to be a little bit of negative, actually, gravitational potential energy, because it's below this point. So this will be the negative m times g times xa. This is the distance xa. Okay. Plus, it's at rest at the beginning, so that's 0. Plus, we talked about there's no work being done by the system or from the outside the system on the system. And then when it gets to B, then you've got the spring is no longer compressed. So spring is at equilibrium, we call it. So it's uncompressed. It goes spring, and it's no longer compressed. Plus, this is 0. And then you've got this. So if this is like 1, 2, 3, 4, and this is 1, then this will just be 1, 2, 3. So some of the potential energy has increased from negative up to 0. And so that's going to reduce some of the energy that was in the spring before it gets converted into kinetic. You could also go from time B, just when it's being launched, to time C, if you want to. You can compare those and use the same energy equation. In this case, it starts with 0 plus 0, so 0 plus 0, plus it's got a big kinetic energy, which again was sort of 3 of these, plus 0, is equal to, again, the spring doesn't compress, but what happens is that all this energy gets converted into gravitational potential energy as it goes up, so that when it ends up, it gets to its maximum height, then you've got 0. So this would be the 1/2 m times v at b squared plus 0 equals 0. It's just 0, 0, plus m times g times h max plus 0. Or if you want, you could even skip the middle phase and just compare A to C, in which case then you've got the spring is initially compressed, and those are sort of 4 things. You've got, it starts off a little lower, it starts off at rest, there's no external work, the spring is uncompressed at the end, and then you've got, again, it ends up at rest. I've just sort of drawn 3 blocks to represent that something is missing, right? I don't know what, like this amount of area. You could have drawn 5 and done 4. But the idea is that once you stick in your equations, you represent mathematically, this is the 1/2 K times it's actually going to be H min, I guess, squared, minus M G H min plus 0 equals 0 plus M G H max plus 0. Yeah, and if we're going to talk about this a little bit, Drew had a good question. If you set y equals 0 to be at position A instead of at position B, you can do this whole thing and you'll still get the right answer. It's only the change in the gravitational potential energy that's going to matter when you're actually solving the problem. Your energy diagrams would look different. They would all be a little higher, but you'd still get the right answer. You'd still get it all correct. So I want to talk in more detail about some of these energies. So gravitational potential energy, UG. The idea is, let's say I have a book that's up on a shelf. There's something different about a book on a shelf as opposed to a book that's on the floor. And another way of thinking of it is, let's say you've got a cup of hot coffee. If you have that cup of hot coffee on the floor, there's something different about that than if it's at the top of a bookshelf hanging off the edge of the bookshelf. I think, especially as a parent, when I think about that cup of coffee at the top of the bookshelf just dangling over the edge, I know something bad's going to happen. So what's the difference? Well, it's kind of like having a spring that's compressed. You've got stored energy that can cause that coffee to fall down and splash everywhere and create a giant mess and a lot of noise and do a lot of damage, right? So this book has some energy, we say, U sub G. And you can change that energy by picking it up and doing something with it and putting it on the floor. But you don't change gravitational potential energy if you go sideways. And there's this idea that it doesn't matter what path you take the book on, this gravitational potential energy, the negative of the work done by gravity will be the same on any of these paths. And so what we say is we just say U sub G is M times the book times G times H. That is the gravitational potential energy. And what really matters is that the change in some y position will give you a change in the gravitational potential energy of the object in the Earth. Okay? So this is actually U sub G is the energy stored in the Earth object system. Keenan is pretty careful to point that out, is that the reason it's coming in there and the reason you have that potential energy is because you're near the Earth and the Earth has this force of gravity on you. And it's approximately constant. So this gives us a whole other way of looking at free fall. If I take my tennis ball and I drop it, then the old way of looking at it is, oh, well, there's a force acting on mg, and so that's the net force. And so there's an acceleration, which is the net force divided by the mass and all that stuff. Well, now we've got a whole other thing, which is that, oh, well, here we have a tennis ball up here. It has some large mgh. It has large gravitational potential energy. So if it goes down here for some reason, it's going to have less gravitational potential energy. So by conservation of energy, it's going to convert that energy up into kinetic, 1/2 mv squared. And so all that's happening is that energy is being transformed from one form to another. You get the same answer, but let's do a poll. You guys are doing something. A small mass slides down the 4 frictionless slides, A, B, C, and D. Each has the same height, and the mass always starts from rest. So rank in order from largest to smallest the speeds of this mass, VA, VB, VC, and VD, when it gets to the bottom of the slide. Okay. You guys want to click in on this? See what you think? Let's end the polling. I can see 83% of you have clicked in out of 434 on the call. These calls are getting sparser. Let's see what the results are. So 60% of you voted for D. And that is the sort of idea that I was going at. So something about me from being a kid makes me feel like you'd go fastest on C, but I think that's coming from, my intuition is coming from friction. I know there's friction on real playgrounds. And so I just sort of think that it would be fastest if you go on C. But in fact, in all of these cases, you've got E initial equals E final. And so E initial, which is going to be, you're going to do kinetic plus gravitational equals kinetic final plus gravitational final. And so if you start from rest, then that's 0. If you end at 0 height, then that's 0. So you end up with m times g times h is equal to 1/2 times m times v final squared. And that's going to be the same for all of these if there's no friction. Robert's pointing out, it's good point. This potential energy equation seems a lot like the impulse equation. They are very similar. The difference is that well, I guess there's a couple of differences. With the impulse equation, there was an x and y component. This one's even easier because there's no components. Energy is a scalar quantity, and it's not, it doesn't have any direction associated with it. Even kinetic energy, which has to do with velocity, it doesn't have a direction associated with it. This 1/2 mv squared, v is just the speed. So it doesn't matter if you're going left or right or up or down. If you're going at the same speed, you have the same kinetic energy. So, but even though energy is a scalar, it can also be negative. So you can, I guess, kinetic energy can't be negative, but potential energy can be negative. You can have negative mgh, just depending on where you set the 0 point. So let's talk a little bit about the 0 point, since we're on this. You can place the origin of your coordinate system anywhere you choose, and you can still get the same answer to the problem, the correct answer. The reason for this is that the physical manifestation of potential energy is always related to the change in potential energy, not the potential energy itself. It doesn't actually matter what your gravitational potential energy is. You can call it whatever you want. I could say, oh, my gravitational potential energy is -10, you know, relative to some spot that's 10 meters above me or something, right? But what matters is that if I change my height, then I'll change my gravitational potential energy. Here's an example, okay? Amber and Bill both have a rock. They both are actually looking at the same rock, and they both have a meter stick. The difference is that Amber's meter stick starts at 0 at the ground, and then it's 1 meter sort of around her waist, and then it's 2 meters just above her head. Bill is holding a different meter stick that has 0 around his waist, has -1 and negative numbers down at the ground, and then 1 above his head. So Amber says it's a 1 kilogram rock. So she says the gravitational potential energy of that rock is 9.8 joules. And Bill says, no, no, no. The gravitational potential energy of that rock is 0 joules. And then so what happens is that the rock goes down and lands on their foot or something, and they go, ow, and they both are yelling for the same reason. Well, for a different reason. What happens in Amber's coordinate system is that it starts off with positive gravitational potential energy and then goes down to 0, and that gets converted into kinetic. For Bill's coordinate system, the rock starts out with no gravitational potential energy, 0. But then its gravitational energy becomes negative. And when it goes negative, then it's decreasing. And so the same amount of energy gets converted to kinetic. It's just two mathematical ways of describing the same situation. It still hurts your foot just as much when the rock hits your foot. Let's do an example. I hold a ball at a distance of 5 meters above the ground, and I release it from rest. How fast is it going just before it hits the ground? Now, I know you guys can all do this using kinematics. You could probably do this question in your sleep. But what I'm going to do is use this new chapter 7 fancy way of doing it, and I'll just show you how it goes. What you do is you define the system is the ball plus the earth. Okay. And so initially, it's sitting here, and then finally, it's going really fast down to the ground. And it gets pulled down. And so V initial equals 0. The height initial is equal to 5 meters above the ground, right? The V final is what you're trying to find. And the H final is 0. And so what you're going to do is your kinetic initial plus your gravitational potential initial, because you're including the Earth, plus the work from outside is equal to the kinetic final plus the gravitational final. And the way this is going to look with your diagrams is that it starts at 0. It starts with some big gravitational potential. There's no external work, and it ends with all of that getting converted to kinetic because it doesn't have any gravitational at the end. So you go 0 plus mgh initial plus 0 equals 1/2 mv final squared plus 0. So I think I can cancel out the, divide both sides by m. So I got ghi equals v final squared over 2. Solve it for v final. I get the square root of 2 times g times hi, which equals the square root of 9.8 times 5. When I plug that into my calculator, I got 9.9 meters per second. Okay. This does not give direction. So that's one of the downsides of using energy. You can get speed, but you can't get direction. So if you'd use the forces, you would know that the net force is down. But anyway, we do kind of know it's going down, right? 10 meters per second seems about right. It was probably about a 1 second fall. It takes about a second to drop 5 meters, so that's okay. So that's how it looks. That was a simple one. Okay, how are we doing out there? Florence, did you have a question?
Hi, Professor.
Hi.
I just had a question about format and then one more question about the speed. So when we do the energy, I don't know if midterm 4 is going to be the one where we have a rubric, but just in case, instead of writing like UG or K, can we write like EG and EK for like kinetic energy, gravitational energy, things like that?
Yeah, sure. We'll use E's with subscripts.
Yeah.
Yeah, that's fine. Yeah. Yeah, I'm sure your marker will be able to figure that out.
Okay. When a ball hits the ground, like right when it hits the ground, is its speed 0?
Good question. So this is when it's just before it hits the ground, right? Mm-hmm. So the very instant just before it hits the ground, I'm saying its height is about 0, but it hasn't come into contact with the ground yet. So there's no force from the ground on the ball yet. So then what would happen next is there'd be this big collision, right? And then you'd have to use the, I guess, chapter 6 stuff to get that.
Okay. Okay, thank you.
Yeah, you're welcome. And Thea, how are you doing?
Hi. I wanted to ask questions about the 4 masses questions, the PHY questions. You go back to the last slide. Like for the 4 mass, like the 4 sticks in the PHY questions. Can you go back to the last slide?
If you could speak just a little louder, it would help me. This one?
Just one more slide before.
The slides?
Yeah.
Yes.
I want to know what is the reference point you're using for the 4 stick because I'm using the reference points, I use the left end of the stick. And I was thinking if the C, when the left end point, when it both hits the ground, then the C, the right end goes up a little bit. So I think it would get a little bit of the potential gravitational energy. So I think maybe C would be a little bit less the speed of the C, because the right end of the stick would get a little bit of the potential gravitational energy.
It's a little hard to picture it. I think what we're assuming is that for all of these things, they start at the exact same height and they end at the exact same height. And all that matters is that is what the change in the height is, right? Maybe I see what you're meaning. Like you're thinking this would be a little higher on C, this one?
Yeah, when the left end hit the ground, then the right end goes up a little bit. So I think
that's a good point.
Potential energy.
Yeah, so I've sort of neglected those little differences, but if that's what you were thinking, that might be a reason. But you get the basic idea, right? If you do change the same amount of height, then you will get the same speed.
Yeah, I got it.
Okay. That's a good point. Yeah, you're welcome. All right. Okay. Yeah, so we're on to elastic potential energy. This is another one. It's going to be called U sub S. So you need to know about Hooke's law. And this is in the chapter, but I'll go through it pretty quickly. I've got a spring, luckily. Idea is you take one part of a spring and you attach it to a wall, something that's fixed. And then you take the other end of the spring and with your finger, you pull it. So what is the work done when a finger stretches out a spring that's originally at equilibrium, when there's no force there, out to distance x? So the work is force times distance. We know that. But the new thing we didn't learn yet is that Hooke's law for a spring is that the force of the finger on the spring is equal to k times x, where k is equal to the spring constant. So different springs have different spring constants. Spring constant, and this is units are newtons per meter. So a stiffer spring will have a higher value of K. So the work should be force Kx times distance, but the problem is there's an integral going on. Keep in mind that the force starts at 0 and then it increases. So you actually have to do the average force, which will be starting 0 plus the final force divided by 2. So that's where there's a half in here. The correct equation for the work done is 1/2 K times x squared, where x is how much you've stretched it. So we say that the work done in the spring is equal to the energy that you're putting in the spring by stretching it. And also you could even do x to be negative. You could push it. And again, you have the same Hooke's law, increasing the force, and you just have the same 1/2 times K times x squared would be the potential energy. So, if you start with the compressed spring and then the ball moves, a spring launches a ball, the compressed spring has some stored energy, which is then transferred into the kinetic energy of the ball. We define these elastic spring or elastic potential energy, U sub S of a spring, to be U sub S is 1/2 K times x squared. So this was a numerical one. You're going to have to actually work this one out. A spring-loaded gun shoots a plastic ball with a speed of 4 meters per second. Okay, so that's when you, I guess, compress the spring by a certain amount. If you then reload it but compress the spring twice as much, you increase x by a factor of 2, then what will be the ball's speed? I'll write down the equations here. I'm seeing that there's sort of a toss-up between, oh, you can't do it again? I see. Looks like you can't re-vote. Oh yeah, we're gonna do this when I'm projecting behind you in a minute. It actually goes far on this. It's really heating up. Okay, let's discuss this. It's been about half and half of either D or E. I think we all believe that the ball will come out faster. The question is it going to be twice as fast or 4 times as fast? Let's share the results. The winner here, 146 of you voted for 8 meters per second, and 145 of you voted for 16 meters per second. So this was a really close one. And if we were all in the same room right now, like Convocation Hall, I would say, okay, let's team up and let's try to convince your neighbor, because half of you voted this way. Anyway, there'd be a big uproar. So you can imagine that. And maybe on Friday, we'll do something like this in the team up. But basic idea is this. So the work is 0, okay, close to 0. The kinetic energy initial is 0. And then what happens is you've got 1/2 times K times X initial squared, stored energy, equals the 1/2 mv final, just after the spring has compressed, but before it shoots out of the gun, plus 0. So what's going on here is you can just solve this out. The 1/2s cancel. You can times both sides of this equation by 2. And you can then solve for, you're finding speed, right? Solve for V final. So what's it going to be? You're going to have K divided by M is equal, or times X initial squared is equal to V final squared. So V final is equal to the square root of K over M times X initial. So first shot, X initial equals, we'll call it X1 or something like that. And so V final is equal to some constant K over M times X1. Second shot, X initial is 2X1. So V final is going to be equal to the same thing times K over M times 2 X1, which is equal to 2 times V final 1. Basically, it was related to the 1/2 mv squared was related to 1/2 x squared. And so when you square rooted both sides of that equation, there's just a linear dependence on how much you compress the ball and how fast the ball goes. So good if you had that. And let me just check my time to make sure I'm good. I want to do yeah, you know what I want to do is an actual example. A moving car has 440,000 joules of kinetic energy while moving at a speed of 7 meters per second. A spring-loaded automobile bumper compresses 0.3 meters when the car hits a wall and stops. What can you learn about the bumper's spring using this information? So initially, what you've got is a car going along with some kinetic initial is equal to 40,000 joules. And then finally, and it's got some uncompressed spring, uncompressed spring, x equals 0. Then it goes some distance, and then it hits, and the spring gets compressed. So this is final. Same car, sorry about my horrible drawing, but you get the basic idea, is that x final is greater than 0. It's, well, x final is not 0. And so what you've got is kinetic initial plus U spring. So you define the system is car plus spring. So now the spring has its own potential energy plus work is equal to kinetic final plus U S final, U S initial. Okay, so you start with some big kinetic, the spring is uncompressed, there's no work done, is equal to it stops plus all of it gets converted to US final. So 1/2, or I guess I'm just going to call it K initial because we actually have it, plus 0 equals 0 plus 1/2 times K times X squared. And X is equal to the 0.3. Okay. So what I got there is I guess I could solve for K if I want to talk about the spring. I would say that K is equal to 2 times this kinetic energy divided by X squared. So it's equal to 2 times 40,000 divided by 0.3 squared. It's a stiff spring. Sebastian pointed out I didn't include the Earth in this system because there's no height change. So I don't need to put in my UG. But you could, but just UG would be the same, right? So then they would cancel out. I'd just say 0. You can do that. So the next thing I wanted to talk about, which hopefully we'll use this little demo back here, is internal energy. If an object slides on a surface, the surfaces in contact can become warmer. Okay, so structural changes in an object can occur when an external force is applied. So the energy associated with both temperature and the structure, any kind of molecular bonds there, is called internal energy. And we call it U sub INT. A thermal camera, like this one that I have behind me here, can detect infrared waves, which are emitted when something has a non-zero temperature. So right now, so I'm sort of glowing. Right now, the camera itself is heated up just because Pius says you're not supposed to plug this thing in for more than like a few minutes. I plugged this crazy thing in for, whoa. I plugged it in for quite a while, so it's really heated up. It's not going to work. Plus, I'm running out of this stuff. See, basically it's all orange. You know what we're going to have to do? I think this is the kind of demo that has to get done at the beginning of class. So at the beginning of Friday, I'll do it once we have a thermal camera. The basic idea is that if I rub an object and use kinetic friction on a surface, then the work that I do there heats up the surface. You should be able to see it. There's Pius. Yeah, you want to come in? Also, I'm running out of this. Oh, unplug it? I really,
They got too hot, sorry.
Okay, we can try it at the beginning of Friday.
Yep.
Okay. Okay. All right, thanks, man. Okay, what time is it here? Hi, everybody. Just trying to work out our demo here. Basically, warm things glow in the infrared, and the higher the temperature, then the more they glow. So you can pick it up with a nice thermal camera. All right, so let's do a quick poll question. I'm alone in the room again. And we'll be pretty close to getting down here. So a car starts with a speed VI, but the driver puts on the brakes and the car slows to a stop. As the car is slowing down, where does the kinetic energy go? It's transformed to A, stopping energy, B, gravitational potential energy, C, energy of motion, D, internal thermal energy, or E, energy of rest. Just going to give you 10 seconds to click into that, please. Okay, so 91% of you are on board with this internal thermal energy. Let me just think about what my plan is for this. Yeah, I think I got some time to do this. Basic idea. Driver slams on the brakes, locks all four wheels, and the car skids 18 meters on a horizontal road. The coefficient of sliding friction between the wheels and the road is mu sub k is 0.8. How fast was the car going before slamming on the brakes? We're going to do this with energy. And so we're going to choose the system is equal to the car plus the road surface. So the road surface is going to have some internal energy. So, and then you can sort of see it. Going to have to draw my little car thing. So initial, so it's going along with some speed vi, which we want to figure out actually. And then it goes some distance d. The road surface kind of heats up. So I'm going to draw the little steam coming off the road. And then finally, you've got this heat in the road, and then the thing is v final equals 0. So the way that looks, you got k initial plus u internal initial plus work is equal to k final plus u internal final. And the k initial is your energy. There's no external work. Your final kinetic is 0 plus this. So all that initial kinetic energy gets converted into thermal energy. And what's going to happen here is that U internal is equal to the kinetic friction force times the D. And F kinetic friction is equal to mu sub K times the normal force. We had that from before. And if the sum of the Y force is equal to 0, this means that normal force is equal to mg. So what that all means, if you combine all these things, that U internal is equal to mu sub K times m times g. And then you've got that 1/2 mv initial squared plus 0 equals 0 plus mu sub k times m times g, times d, right? Times d. So solve for v sub I. And you get v sub I is equal to the square root of d. I think there's m's on both sides of that equation. So m there, and there's an m there. Square root of 2 times mu sub k times g times d, which is equal to 2 times 0.8 times 9.8 times the 18 meters. So V initial is equal to 17 meters per second, which is about 60 kilometers per hour. City speed. Okay. So that sort of takes us up to the end of 7.5. I would like you, before Friday, to read about 7.6, this work energy principle, and 7.7, which talks really about elastic and inelastic collisions. I'm going to try this thermal camera again on Friday morning when we start the class, when the camera is still nice and cool. Please plan to meet up with your practical pod if you can, if everyone can show up for that, that's always fun. But I will start breakout rooms in the help center if you want to use that way as well. That's another place you can meet up. But we have limited breakout rooms in there. So try to use your Microsoft Teams. I'm going to stick around here till around 12:30, and then we'll switch over to the help center. Thank you very much and have a fantastic day, everybody. I'm going to turn off the record, and then I'm going to grab your hands here.